Are you going to use it? I guess.
Nothing showing up.
Oh, really? No. I'm too patient to get it off because I'm not like
That's kind of annoying.
what it was. I mean,
Too much work.
yeah, it goes
It's fine. It's fine. I got it. I got it.
Wait, so can I see this?
Um, make this full screen. Awesome.
Yeah. 10:30. Yeah.
All right, I'll start in like 1 minute. This one further? Okay. All right. Hi, everyone. Welcome back. Yay. So, how has your first week been? Finalized classes, everything settling down? Awesome. Okay, so it started to rain today. I was scared that some of you might not show up, but it stopped raining, so glad all of you showed up. So today we're going to talk about streams. For context, I have like about 100 slides here. Last quarter, I had 300, and a student wrote on the feedback form that this was one of the most stressful experiences they've ever had. So yes, today is going to be very, very manageable. All right, so we're going to talk about streams. What we're going to cover today, we're going to first do a high-level overview of what a stream is and why streams exist. Then we'll talk about the most basic kind of a string stream. Then we'll discuss state bits and talk about I/O streams. At the very end, if you have time, I'll do like a 2-minute thing about manipulators. They're not super important. Okay, but before I get to that, I realized that Keith has not taught what a string is in C++. So I'm just going to give you like a quick crash course on what a C++ string is. All right, so let's see. Okay, so in most languages, how do you denote a string? How do you create a string? Yeah. Mm-hmm. Sure, yeah, so string, some variable name, let's say str, equals, and then you can declare whatever you want here, so hello world. Okay, so yes, this creates a string object, string, and then the string itself holds hello world. So if you try couting here, you would get, it would print the string to cout, okay? Some weird caveats of strings, let's see. One special thing about strings is if you say you wanted to get a single character, anyone know how to do that? It's the same as in Java and Python. How do you get a single character? Yes? Yes, okay, yeah. So in Java, you would use .char@, right? Yeah. Mm-hmm. How about in Python? You index it, right? Okay. So in C++, you do the indexing thing where you do like, suppose you wanted to get the first character. What would this print? The E, right? Because don't forget, strings are zero indexed, kind of like all the other data structures. So if you print 1, you would get E. Okay? Unlike in Python, you can't do weird like -1. You can't do that. Okay? In C++, you can only index based on the actual indices over there. What else? How would you modify like a character? Suppose I wanted to change hello world into like change the E to some other character. Yeah. Mm-hmm.
Do str equals index like str0 plus whatever you want plus the rest of it.
Cool. Yeah. So So in Java, if you wanted to change if you wanted to change a character, you would have to do something like this. String, you do a substir from like 0 to 1 plus the new character, let's say I, plus another substir to somewhere else. Okay. But in C++, this is really neat. In C++, this string, you can treat it exactly as if it was an array. So you can just literally do equals I. Okay? So because in Java, because the string object is a little bit more like safe, so you can't do stuff like this. But in C++, you can treat the string as if it's just an array of characters, and you can set it directly like this. Okay? Any questions? Yeah, question, yeah. Good question, yeah. So when you index into a string, each of these characters, these are characters. So you would set this to be a character. Yeah, that's a really good point, though. A lot of, especially if it's your first time in C++, you might try this, and you'll get a compiler error. Yeah, and the compiler error is also really confusing. So yeah, good catch. All right. Final thing that I want to briefly mention is if you pass in well, I'm trying to decide how to motivate C strings. This literal over here, this is actually a C string. There are two types of strings in C++. There's a C string and a C++ string. Okay. A C string has type char star, or char bracket something. And then a C++ string is an actual like real string. Okay. Generally, always use C++ strings, and to use a C++ string, basically actually declare a string object called str. Cool? All right, that's all we need for today. Everything else you'll learn on Friday with Keith. Cool, let's talk about streams. So why do streams exist? Well, we often want our streams to be able to interact with external devices. Here are a ton of external devices that your programs might want to interact with. Some of the most common ones, a keyboard, so the console and keyboard, these are the most common ones that you'll see. In fact, in CS106B, you already saw cout. Cout is a stream which is connected to the console. So if you print something to cout, you'll see it on the console. These streams are also tied to like the keyboard. So if you type characters in, these are connected, the keyboard is connected to a stream inside. You can also do files. We won't cover files today, but Keith will cover files tomorrow. Okay, so tomorrow you'll learn how to read stuff from a file. You'll learn how to write to a file. These are also done using streams. We won't cover these two because these two are fairly advanced. You can write, you can have different programs running at the same time, and they send messages to each other. They're communicating to each other. That uses this concept called pipelines. You'll learn that in CS110. Really cool, but basically you can also use streams to be able to send stuff to other programs. Finally, streams are also used to do networking. We're not going to cover that, but you can take CS144. You'll learn how to send, how the stream itself, you can send stuff to the stream, and the stream will manage like sending the stuff to some other server. Cool? The cool thing about streams is it is a unified interface, right? There's there's a stream. Streams you can do all sorts of things, and then the way to use a stream is really similar for all four. Okay? For example, you all know how to print stuff to cout. You pretty much do the exact same thing for the other ones. Okay? I personally like to call that the alligator operator. It's the two less than signs, right? That's how you print to cout. That's also how you print to other programs. Okay? So the point of the stream, it provides a unified interface for all sorts of interactions. So just to think about, suppose you had like an object called date. We haven't covered objects yet, but I assume if you were from Java or from Python, you know that these objects exist. How could you print, suppose you wanted to print this object to the console. How would you do that? Well, there are like two main steps you have to do. One is you have to first convert this like information variable type of object in your program, and you have to convert that into a string. There's no direct, easy way for the computer to know, okay, this, if you convert it to a string becomes that. So this is the first thing you have to manage, type conversion. And then the second part is then you have to actually take that string and somehow write it to the console. Make sense? Okay, which operation do you think is harder? Any guesses? Which one seems harder? Okay, so type conversion seems kind of complicated, right? You have to like read the fields and do that. But do you know how to do that? If I give you an object, can you turn it into a string? Probably, right? You can just write like a table. 1 is January, 2 is February. Just have that table over there. You can read the month, find what month it is, find the date, print it, put the date, put that into a string. Okay? So this is kind of complicated, but you all know how to do this. The other part, actually writing to the console, that's fairly complicated, right? Like, how do you actually touch what the console is doing, right? You haven't learned anything in, probably even in Java, right? You haven't learned how to actually put stuff onto the screen on the console, okay? So that second part is the hard part, and the goal of streams, okay, let me let me just do another example. Suppose you wanted to read a double from a file. Well, there are two steps. You'd first have to read the string representation from the file, because remember, a file is just a bunch of characters. Then you would convert that into a double. Okay, you can probably do this. This is kind of annoying. You have to first find where the decimal point is. You have to find all the characters. You have to turn them all into digits. But you can do this. How do you actually read a character from a file? That's kind of complicated. So, yeah, again, these are the two challenges. And the point of the stream is it provides like a unified interface for the entire thing. Instead of having to worry how do you actually read or write something, you can just treat the stream as a buffer of characters. Okay? Don't worry about how the stream actually takes your characters and puts them into the console or whatever file you're writing into. You can just treat the entire thing as if it was a large array. Okay? And then the interface for interacting with the stream is using the output and input operators. Okay? So, yeah, for example, if you're printing to see out, you just put something, alligator see out. And then what cout would do is inside cout's buffer, it would write whatever characters, like 3.14, into the buffer. Somehow later, the cout buffer will transfer the stuff from the buffer to your console. All right, same for the reverse direction. You don't really know how your stream is reading from a file into the buffer, but you know that there's a buffer in there, and you know that you can just read stuff from the buffer. Okay, so all you have to worry about is this operation. The stream itself takes care of everything else. Okay, any questions at this point? This is kind of a high-level thing. It's not like this is fairly abstract. You actually don't know how this works yet. So we'll get into an example very quickly. Okay. First, let's talk about a string stream. String streams are easy because they're not tied to anything. Okay. They are basically, it only does this conversion itself. Okay. If you write stuff to the string buffer, the stuff just stays there. It's not transferred anywhere else. Okay. So let's do an example. Do you all have this code pulled up? If not, that's totally fine. You can find someone sitting next to you who does have it pulled up. I like lectures to be sort of interactive, so fill stuff in as you go along. And as I wrote over here, I wrote a lot of stuff down there. You can take a look as to what is down there, but you can just call these functions and see what happens. Again, follow along. Try to type in some code. You can also try experimenting with different things. If you notice anything that you didn't expect, ask. Okay, so the first thing is we're going to try just doing some things with string streams. The first thing we have to do is how do you construct a string stream? Well, to construct a string stream, there are two kinds of string streams. There's an input string stream and an output string stream. Let's first create a output string stream. Okay, so we've just declared an output string stream. Actually, we will learn about why that's an error later. Yeah, so we've declared an output string stream. In fact, just to make it fun, I'm going to first put something inside the string stream. So let's say Ito and green tea. Okay? So what you should imagine right now is once you've created the string stream, you have a string stream, and inside its buffer, it already contains these characters. Make sense? Okay. This is an output string stream, which means you can write stuff to the string stream, but you can't read from it. Okay, so suppose I write something to it. Let's say I write 16.9 ounces. Actually, before we even do that, let's try running this, okay? So streams have a special operation where you can essentially dump whatever is in the buffer, dump it into, like, create a string from that. So for example, I can do something like oss.str. This method converts whatever is in the buffer into a string. Okay? Does that make sense? So what do you expect is printed over here? Yep, Ito and green tea, because we've constructed a string stream. Inside its buffer, we start with these characters, and we just immediately convert the buffer back to a string. So it should still be Ito and green tea. All right, any questions at this point? All right, so now we can actually write stuff to the OS stream. So for example, we can write 16.9 ounces, and then we can try printing out oss.str again. What do you expect is printed? Yeah. Mm-hmm.
I have a question. So when you create an
Mhm.
or will all of them share a single shared location?
Good question. So when you declare, the question was when you create a string stream object, does it have its own buffer, or like when you create many string stream objects, do you get like the same buffer for all of them? All right. The answer is that each string stream gets its own buffer. Okay. So you can see that we actually have two streams going on here, right? We have the O string stream. This is a string stream, and we also have a cout. Cout is also a stream. Okay, these two buffers are not, they don't share stuff with each other. So we can print stuff to cout, and our OSS is still doing stuff. Okay, good question.
So
And
why would you use a stream rather than a character buffer?
yeah, good question. Why would you use a stream instead of a character buffer? As we'll see very soon, writing stuff is kind of nice, but then the real power is when you're reading stuff from the stream. The stream itself will automatically like find the characters for you. It will do type conversions for you as well. Okay, so for example, if you wanted to read an int from a buffer, that's kind of hard, right? You have to like find where the spaces are. You have to take the characters, turn that into an int somehow. If you just do it with a stream, you can read the int directly, and I'll show that very soon. Okay, go ahead.
Oh yeah. Oh no, that's a great question though. Yes, like whenever we teach you guys something, it's always good to sort of ask, why would we use this versus something else that does something similar? So yeah, that's a good question to keep on asking.
All right, so can you guess what is printed here? Any guesses? All right, if you're not sure, you can always run the code. Let's see what happens. Okay, so what just happened? Yeah.
Same length.
Okay, so same length. What changed?
It's like the 16.9 ounces just overrode.
Mhm.
It's in the same positions of the original.
Exactly. The 16.9 ounces, we basically overwrote the buffer that was inside. Okay? So this is a really important concept, which is the buffers themselves. If you looked at the slides over here, you'll notice that I had an arrow over there, which should show like where the current position is. All right? That determines where everything is being read and written from. Okay? As you write stuff, the position pointer just keeps moving downwards. Initially, when you constructed a string stream, it initially starts at the beginning, which is why we overwrote the buffer. Okay? But you don't have to memorize any of this, but if you wanted to start a string stream at the very end, you can do something like stream. You can provide a constant called ATE, which stands for at end. Stream. It's not defined. Really? Stream. That should work, yeah. Okay, that's odd. Oh, stream. Oh, there we go. Thank you. Yeah, okay, so you can do this, and then if you try running this, the position pointer starts at the very end. And of course, this file is not found. Okay, which is probably what we wanted initially. Now the position pointer starts at the end. Okay, any other questions? Yeah.
Just to clarify on some of these slides, you're saying that the 16.9 inside of that string, that's still being represented. It seems in these slides that it's somehow represented as a double in the string stream, but is it actually being represented as a double, or is it being stored just as, the characters 616.9?
Mhm. Yeah, they're being represented as characters. Which slide are you referring to? This one?
Looking at slide 18.
18, okay. This slide? Yeah, so don't forget, the stream abstraction is over here. That's the stream abstraction. So this string representation, this is actually like what the buffer is written as, and the characters are stored inside that buffer. Yeah, this variable you see over here, this is what is in your program and what you're writing to the buffer. I think I know what you mean. Do you mean like here, instead of writing this, we just write 16.9? Like, can we try this instead?
Sort of, yeah.
Mm-hmm.
What I'm trying to get at it's not actually doing the number to string conversion. It only natively takes strings and stores them at string, regardless if that string contains a number or not. Is that correct statement?
Good question. So one cool thing about string or any streams is they do the conversion for you. So you can put any type which supports insertion, and it will convert whatever type into a string before
so that
putting
will
it.
work?
This will work, yes.
Okay, thank you.
Okay, so if we put this instead, the 16.9, they're converted into individual characters and placed into the buffer. Okay? Cool. All right, so there's not much to O-string streams, but they're just fun to play with. Let's try an input string stream. Let's start with the same thing. Ito, actually, let's do 16.9 ounces. Okay, so why input string streams are cool is they do conversions for you. All right, so suppose I wanted to read whatever is at the beginning, so 16.9, and I want to actually use that inside my program. Okay, what I can do is I can just create a variable double amount. Let's also create a string called unit, and we can actually just directly extract the double, and then we can extract the unit. Okay, so notice what's going to happen is we create an input string stream, which it has these characters in the buffer. The position starts at the beginning. When you call this operation, what the string stream does is it moves the position down as far as possible until it reaches a white space, and it grabs whatever characters it went through, and it turns it into whatever type you wanted it to be. So here, the position started over here at the very beginning, and then it moved down, reading as much as possible until it reaches a white space, and then it turns these characters that it read through into whatever type you asked. So here, it turns the 16.9 directly into a double with the value 16.9. Okay? How are we so far? Does this make sense? Okay, and just to prove that it is a double, let's try printing amount over 2. And what do you expect to be printed? 8.45 exactly. All right, so if you do that, 8.45. All right. Important thing is that the type that you read into is important. Okay, so if I turn this into a string instead, oops, this would still work, except when you do ISS and it tries to grab a string, it grabs the 16.9 without turning it into a string. Okay, so which is why this amount over 2 doesn't work, because amount is a string. Quick question, what if I did this? And I printed, oops. Okay, what do you expect to be printed? I heard someone say the answer? 8, yeah, because it goes forward and it tries to extract as many characters that make sense to read into an int. It sees the decimal point and it's like, okay, the decimal point can't be part of the int, so we must stop here. And it grabs the 16, turns it into an int, puts it into amount, so that's why you get 8 over here. What is unit? What would unit be? Okay, I heard 0.9 and 16.9. The answer is 0.9. And the reason is because the position has moved down to this position, right? It tried to read the 16 in, so the position moved to that position. And then when you try doing this operation, it reads up to the next white space. So it reads this. Okay? So we try it out, and it works, probably. Yeah, so 8, and then followed by a space, followed by 0.9. Question, yes?
So the white space is not the only delimiter, right?
Mm-hmm.
So you can have like a dot or like a comma.
Good question. So you're asking like when you do the arrow operation, what is the delimiter?
Yeah.
Okay. Yeah. Good question. So if you're reading a string, so if you're extracting stuff into a string, then the delimiter is going to be a space. Okay. In fact, on not just any space. Here's a slide that shows exactly what is a white space separated token. If we try to read in, suppose these were strings, and if you tried to read in string by string by string, the first one would be token. It would skip the \n, that stands for new space. Ounces with the period. It reads that single period as a token 3. it skips these backslash key, that's a tab, a bunch of new spaces, it skips everything, and it just reads the next one. Okay? Yeah, yes, it reads a white space separated tokens. Other questions? Was there a question in the back? All right, awesome. Okay, so types do matter. If you tried, the second part answer to your question is if you are reading into various like other types, not strings, then it reads up to as much as it can while the type still makes sense. So if you're reading an int, the 1 and the 6 make sense as an int, but the period no longer makes any sense, so it stops there and it reads the 16 as the int. Okay. Okay, now this should bring up a lot of like questions, as in like, okay, it's trying to read into an int. What happens if it can't? Right? That should be a question that you immediately try to think of. What happens if it can't? And we'll get to that very soon. You had a question?
That was what I was going to ask.
Okay, exactly. Okay, cool, awesome. Yeah, so just a review. If you, the alligator operations, it takes the variable, converts it into some sort of string character form, inserts it into the buffer, and that's it. So you can chain these operations. So if you chain the operations, it does the first one first, then it does the second one. If you chain the bottom one, it reads into the first one, then it reads into the second one. Okay? Later, I have a question about why this works, right? Like, when I took this in 106B, I always had a question, which is like, what exactly does this thing do? This seems like a really weird symbol. You can't do this with any other objects, right? Like, you can't read into a vector, you can't read into some other object. Why does this work? And specifically, why can you chain it like this? Okay, actually, I kind of wanted to answer the question right now. These are called operators, and we'll talk more about operators later, okay? But these operators, they're specifically defined for, okay, what happens if you use that operator with a stream and some other object? And here, whoever wrote the stream library said, okay, you're supposed to turn the right object into characters and insert it into the left object's buffer. Okay, obviously this only makes sense if the left object has a buffer. Why can you chain them? By whatever order of operations it does the left one first. This left operation it returns the OSS itself. So what actually happens here is, suppose we tried chaining this result. This would work. What would happen is after this initial operation is done, this would return ISS itself. So this would collapse to this. Okay? The alligator operator returns the stream itself, which is why you can chain them as much as you want. Any questions? Cool. All right. Let's skip. We answered these. Is there a string stream that can do both insertion and extraction? Yes. It's called a string. It's just called the regular string stream, not the I string stream or the O string stream. You can Google that. It's kind of neat. There are these things called string positioning functions. They're kind of low level. They're kind of boring. Essentially, you can move the position pointer as much as you want. You can easily Google them. You can figure out how these work. All right, there's also, you can actually access the buffer itself if you wanted to. And we're not going to teach that because that requires understanding of pointers, but just FYI, those exist. Cool. All right, so believe it or not, you actually know enough to implement your first Stanford library function. Okay, so first Stanford library function, string to integer. Okay, what does string to integer do? It takes in a string, converts it to an integer. If it fails to do that, it throws an exception. Okay? Now, don't worry about the throw an exception part. On your own, or with the person next to you, try to figure out how you would write this function. Okay? You know enough to write this function. And it's only 4 lines long. Go ahead. Oh, can't put that prototype. Dang it. Okay, so everyone has to do that too. All right. I think we can continue. Okay. So, any ideas? Anyone want to volunteer an idea? Any ideas? Any ideas? I'll give you a hint. You need string streams. So what do you think that the first line is?
IS string stream.
Okay, declare an IS string stream. What do you put in the parameter? S? Okay, great. So we're taking we're taking S and we're creating an I string stream with where the buffer characters are the characters from S. Okay, what's next? Sorry? Okay, declare an int here, because we're turning this into an int. Yeah, so int result. Next. Yep, read from ISS, read an int. Lastly. Okay, yeah, so cout would be printing it out, but here, this is a function, so we're just going to return the result, okay? Yeah, pretty simple, right? Okay, so type that in there, and so what I've done is down here, I've written a function, string to integer test, which lets you type in different integers, and it calls your function for you, okay? Don't worry about how this works, you'll learn about that next week, but yeah, so in the main function, try calling string to integer test. And I made a little bug. I forgot to declare a prototype for this. So you have to copy this, put it at the very top. Okay, I forgot to declare a prototype. So make sure you do that. And then you can try calling this function, and you will get. And something like this will pop up. Okay, so it prompts you to type an integer. Let's say 30. Okay, and then what it says, okay, you typed in 30. I'm going to convert it to an integer. This is still 30. Half of 30 is 15. Okay, so here we can see that it successfully read in the string 30, turned it into an int, and divided it by 2. Make sense? Okay, let's try other things. 7. Okay, so you typed in 7. Half of that would be 3. So here you can see it's turning the string form of 30 and 7, turning it into an int, and then having it so it prints out. So it prints out half of that. Okay? Does this make sense so far? Okay. Well, why don't you test it out? Try to break the program. Try to do anything you can to just try to make it do something incorrect. Okay? It's not hard. Yes?
Type in A, B, C, D. Or just A.
Sure. Okay, so if you type in A, it thinks that you typed in 0, and half of 0 is 0. Yeah. So that does break the program. Anything else you can break? Special characters, sure. Yep, it also breaks the program. Any other ways to break the program? Enter, okay, yeah. So if you type in enter, it thinks it's 0. Oh, yeah, so, good question, okay. You might not get 0. Can I have your attention? Hi, everyone. All right. If you type in enter or if you type in something incorrect, you might not get 0. All right, and the reason for that is because, did Keith talk about this yet? If you declare integers without initializing them, they're just random junk. Okay, so this result is not necessarily 0. It's whatever random junk is in the computer when you declared it. So when you print out, what happens is this line doesn't do anything if it can't read an int. And then when it returns result, it returns whatever junk was in result. Okay, these are uninitialized values. They're bad. They cause severe security issues. Ask Anna. Yeah. Other fun things to try. What if I typed in 8, so a valid int, and then I typed in another int? What happened? Maybe I should try like 9 and 3. It basically just read in the first one, it ignored the others. Okay, what if I did what if I did a non-valid character and then a 9? What happened?
You only run the first.
Yeah, it ran the first one, figured out, oh, it's wrong, so it just doesn't do anything. Okay? So we're going to try to fix that because, yeah, so this is what usually happens if you try to use cin without learning how streams work. Basically, on your first assignment, you'll pass all the regular tests, and then when they try to test your program using erroneous inputs, you fail all of them. So don't use cin in CS106B. Okay? Or exams. Let's see, I have a lot of windows. Okay, so here's the first attempt. The problem is, what if this operation fails? Let's talk about state bits. There are 4 bits which indicate the state of a stream, okay? And they're color-coded like here. There's a good bit, a fail bit, an EOF bit, and a bad bit. Okay, just a quick overview. Good bit means everything's good. Fail bit means the previous operation failed. EOF bit means the previous operation reached the end of whatever buffer you have. And the bad bit means something bad happened. Pretty self-explanatory. Well, except the EOF and the fail. All right, so one thing that you notice is that if fail happens, or if any of the other bits are on, all future operations are frozen. Okay, what does that mean? That means if this operation fails, then the fail bit is turned on. You can try to do random stuff with this, like valid, invalid, whatever. All of those operations will not do anything. Okay? So these bits are very important. They indicate what is happening to the stream right now. Okay? So common reasons why a bit could be on. The first one, nothing unusual. If all the other bits are off, the good bit will be on. Fail bit, most common one is type mismatch. What does that mean? Kind of what we just did, right? When you try to read an int, but it can't read an int because it's not an int. Okay? If that happens, the fail bit is turned on and future operations failed. EOF, when you reach the end of the buffer, we'll see that later. And then bad bit is rarely on. If the bad bit is on, then something really, really bad happened. There's probably some internal error with the program. You probably can't recover from a bad bit issue. We can definitely recover from the fail bit and the EOF bit. Okay? Now, important things about state bits, and this is not intuitive. Good and bad are not opposites. Okay? These are also like philosophical questions to think about. Good and bad are not opposites. All right? Good and fail are not opposites. Okay? When you get your winter quarter exam grades, remember that good and fail are not opposites. Okay? So, just because you want to check if you failed doesn't mean that it's actually good. So if you check at your exam grade, you did not fail your exam, that does not necessarily mean you did well either. Okay? Good and fail are not opposites. Good and bad are not opposites. Yeah, but then the most important ones we care about are fail and EOF, which means you rarely want to check good, because good is not the opposite of fail, good is not the opposite of EOF. Okay? Cool. Let's try looking at state bits. And to do that, I wrote a cute little function down here for you called there's a cute little function down here called print state bits. Okay? And you can quickly read it. What it does is it prints the state bits. Okay? Something to note is I use this thing called the ternary operator. You don't have to really understand this. Keith will actually teach this. Keith is the only lecturer who will teach this. Yeah. Basically, the ternary operator is a really short if-else statement. Okay? Understandably, some people hate it because that does not look like an if-else statement, but Keith really, really loves it. So yeah, you'll learn more about this. It's nice in that if you have to do something like this, you can replace it with one line. Okay? The fun, should I tell the fun fact? No, I'll save it for next time. Cool. Cool, let's see. Okay, so what we're gonna do is we're gonna just try inside this function, let's try printing the state bits. So print state bits. Okay, and you have to pass in whatever stream you want to look at the state bits of. So here we want to look at ISS. Okay, so I'm gonna print the state bits here. I'm gonna print the state bits after the read. I think that's it. Okay, so we're gonna try to print the state bits immediately after it's constructed, and print the state bits immediately after you try to read from it. Okay? All right, so try typing that in and try running the program, see what you get. Okay, so let's try a regular operation. 137, Keith's favorite number. Okay, so does this make sense? Initially, the good bit is on. After the read, the EOF bit is on. Does that make sense? Okay, that intuitively makes sense, right? Initially, everything is good. When you read something, you reach the end of the buffer, the EOF bit is on.
Sorry, can you go back and show how you do that again?
Yeah, sure. So it's basically, it's the 4 lines of code, but you call this function print state bits, which was defined below. You pass in whatever stream you want to look at the state bits of. Okay? Any other questions? Question, yeah?
So will the first one always print good? Because it would then include that.
Yeah, this is usually going to print good. The only exception is if the constructor somehow failed. I don't know how the constructor would fail here. If you passed in some weird thing, maybe. Okay? All right, everything good? Okay, now what I want you to do is I want you to keep testing this and try all the other bad inputs. See what happens to the error bits. I'll give you like 30 seconds. Just test anything you can think of. See what kind of error bits you can get. I'll give a special prize to whoever can turn on the bad bit, because I haven't figured out how to do that. Okay? I haven't figured out how to do that without actually crashing the computer. So see if you can do that. Oh, sorry. Here. Here's the code. Yeah, question?
What happens if you input a number that's bigger than the range of integer?
Good question. Do you want to try that? Yeah. It's not working? Okay. Oh, okay. I'm not sure. Close enough? I guess it gives you int max. Here's int max. Yeah, so I guess it interprets it as int max, which,
Turns on fail.
yes. So it probably is able to sense that you went past int max. Pretty cool, right? It's pretty smart. Okay, what have you tried? Okay, has anyone been able to turn on the fail bit? Okay, what did you try?
Try anything that's not an integer.
Okay, opposite of fault. Yep, so you can see the fail bit is turned on. Any other ones? Yeah,
So the reason why you aren't reaching the end of it is because you are failing out on A and not continuing on to the rest of the buffer.
right. When it determines that it's going to fail, it stops. It returns to wherever it started, and it says, "Oh, I failed."
So why, if you enter only a single character, it'll pop out fail, not end, and if you do blank, you'll get fail and end.
So if you do a single character, it looks at the first character and it says, "Oh, that's not valid," it moves the position pointer back to where it started.
I see.
Yeah. hmm When the buffer is empty, it's able to sense that, and it's like, okay, and it doesn't do anything. Okay?
I see. So upon a failure, you move your pointer to the zero to the very start.
Back to right before the operation began.
I see. So
Yeah.
you had like 2A,
Mhm.
it would bring it back to the 2, right after the 2 and before the A.
Yes. Okay. One thing to note is even if you type in the empty string, the EOF bit is not on yet. EOF is only on if you try to read past the end. Then it turns on EOF. Okay? So very common bug. If you test EOF, you have to be careful with that, which is why I don't recommend checking EOF. Okay, anything else? Is anyone able to get the good bit on at the end? Yeah,
You put something else after integers.
So 8A. Notice that the good bit is on at the end. Okay, so now the question is, okay, are you able to check for errors? Given that you know the bits, can you check if an error has happened? So after the operation, how would you know if string to integer was successful? You get what, sorry?
Get the E.
Okay, exactly, you get the EOF bit, okay? You get the EOF bit, and in particular, you don't get the fail bit. You don't get the fail bit, and you get the EOF bit at the end, okay? Yeah, it can't just be EOF though, because you have to care about this edge case. You can't have the fail, and you want the EOF. Yeah, question?
Earlier you said something about don't check the EOF flag as a check. Can you repeat what you were saying about that?
Sure. This is more important when you get to files, when you try to read from files. Sometimes you write this condition. While we're not at the end of the file, try reading a character. Okay, so you're gonna keep reading, you're gonna keep reading, you're gonna keep reading. And then what happens is if you check EOF, it's not gonna actually be able to do that until it runs one more time and that fails. Yeah, so depending on how you structure your loop, it's kind of like an off by one error where if you have to wait until EOF, that kind of, it kind of goes past the last character. Okay? Depends on how you structure your loop, but oftentimes you get like a bug that way. I don't have an example right now, but I'll pull up an example and post on Piazza. Yeah. Okay? All right, we might go a few minutes over time, but I hope that's fine because this is cool, right? This is pretty cool. No? All right. Okay, I'll be honest, streams are like not my favorite topic, but they're my fanciest slides, so I kind of have to teach it. Okay, so, by the way, one way to do with this is to check if the EOF bit is on, okay? Another way to do it, which is the way that I prefer, is, okay, try reading a character. Make sure that the fail bit is not on. Then, try reading a single character. Make sure the fail bit is on. Does that make sense? Let me type that out, and then let's try to understand why that makes sense. Okay, so I'm going to try this operation. If the fail bit is on, then that means something really bad happened. Throw an exception. I'm going to throw this thing called domain error. Don't worry too much about what it is. It's just throwing an exception. Error. Okay. This check is not enough because we saw in the example where you might have the good bit still on, and that's not good, right? So we can also check, okay, you also want to check if, try reading another character. Remain if ISS, remain if ISS dot fail. Now we do want to fail. So if it does not fail, then throw std domain error. Okay? All right. Look at this code one more time and explain it to the person next to you. And I go 5 minutes over. That's fine, right? But that's the nice thing about the buffer time. Yeah. Better error messages? Okay. Okay, that's a good point. Okay, all right. To test your understanding, what should this error message say? What's a more informative error message?
No valid int at beginning.
No valid int at beginning. Okay. What should the second error message say?
More than a single valid int.
Okay, more than a single valid int. Okay, or even just because technically you can have one valid int and then an invalid int. So I guess you can reword it as like just there's stuff after the valid int. Okay, cool. Yeah, awesome. So yeah, this is how error bits are helpful, and this is how you can be able to check for errors. A question? Yeah.
Really quick, why wouldn't you just do ISS.n?
ISS dot. Oh, EOF? Yeah. Good question. So yes, you can do that for this example. Yeah, this would work. So you can also do this. The reason I prefer the other one is that one is more later on when we get to IO streams. IO streams, it's kind of rare for EOF to be on. Yeah, because there's scenarios where you type in a bunch of stuff and it only reads like a little. Yeah, so I preferably don't like to use the EOF, but in this example, you can definitely use the EOF. That would work. Okay, I just want to make it more consistent across. Oh, here you want to check if EOF is on. If it is on, then you want to throw the error. No, actually, no, sorry. If it's not on, then you want to throw the error. Okay? Cool. We're out of time, but since the class technically ends at 2:50, I can go like a little over, right? Okay, if you need to leave, feel free to leave, but, okay, wait. Okay, so just as an example, yeah, here was the example we did. Also, just as a shortcut, this thing, someone remind me, what does this operation return? The stream, right? Okay, and funny thing, this stream can be reinterpreted as a Boolean, where the stream itself is translated to true if the fail bit is off. Okay, that was a little confusing. Essentially what I mean is, instead of checking this, we can also just put this expression directly into here. So this operation returns the stream, which is converted to whether or not, which is converted to if the fail bit is off. So we can put this into here and do something like this. Okay? And then here, instead of reading in a single character, so char remain, we can put ISS read a single character. Make sure that it's off. If it is on, so if this is successful, then it returns this. Other way to think about it is this operation returns true if the fail bit is not on, and it returns false if the fail bit is on. Okay? It's just like a more compact way to write this. When you learn about file streams in 106b tomorrow, you will see this idiom, this C++ idiom, appear again. Okay? You'll probably see it in this context. While file something. Yeah, you'll probably see in this context. And I just want to point out here that this is equivalent to fail is equal to not fail. Okay, cool. I can't talk about any of this. I'm so sad. Okay, well, okay, so lecture is technically over. This is technically optional material, so if you want to stay and listen to it, that's totally fine, okay? And I do mind if you answer questions, if students have questions.
Yeah, and quick question for people. Was anyone else not able to download the source code from the website? Okay, so just a couple in front. Yeah, okay, sounds cool. And we discussed it.
Okay, this is optional material, so if you want to leave, feel free to leave. But technically, I have you all until 2:50. I'm going to repeat that many times in the quarter. So, I'm going to keep talking. You don't have to stay for this. This is optional. This probably won't help you on an assignment, but it will give you something good to talk about at cocktail parties. Okay, buffering. All right, so yeah, question, yeah. The main function. the main function?
Yeah.
Okay.
On that line, it says use the unlimited
Mhm.
string to be tested.
Yes, good point. And the reason is because I forgot to declare the function prototype at the top. So just copy this thing at the very top, copy this line, and you'll get the very line. Quick question, do you all have class at 2:30? Because I'm a little sad. Okay. All right, so we're going to try this experiment. We're going to try to we're going to print to cout, CS. Then we're going to print 106. We're going to print L, and then we're going to print endl. Okay? I'm not going to do the flush yet. I'm not going to do the endl yet. Okay? So basically, it's going to try to, this is going to be cout, so it's going to try to print cout. And it's going to do some mindless work. Then it's going to try to print 106, do more mindless work. We can remove this mindless work. It's going to print L, do more mindless work, and then at the very end, let's do the new line. Okay? So the mindless work takes around like 2 or 3 seconds. What do you expect is printed? Okay, this is kind of hard to explain. So probably what you're thinking is it's going to do CS, a few seconds, 106, a few seconds, L, a few seconds, new space, a new line. All right, right? That makes intuitive sense. Does that actually happen? Oh, sorry, called the wrong thing. Up here called, yeah, you don't have to try, you don't have to type this in, but I'm just gonna type this out. All right, watch what happens. Wait, so what happened? Yeah, it printed out all at once. Exactly. Okay? And this is the cool thing about the buffer itself. When you send something to cout, it puts the stuff into the buffer, but it doesn't transfer the stuff in the buffer into the console until later. Okay? Any guesses as to why that might be? Why would you not transfer every time you got the chance?
I'm imagining there's some overhead to grabbing the console and printing it out so it can queue up a bunch of stuff and then over the
Yes, exactly. Okay. Every read and write operations are expensive. They're kind of slow. All right. So every time, if you try to do that every time, that kind of will slow your program down. In fact, cout is a buffer stream. There's also another stream called cerr. It's used to print error messages. Did I spell this right? E-E-R? No. Oh, STD. STD. Okay. Okay. There's another stream called cerr. It's used for printing error messages. You can imagine error messages are so important that that there's no buffer. Every time you send it stuff, it moves it directly into the console. Okay? Did everyone see that? CS immediately, then 106 immediately, then L immediately. There's no like wait until everything's done, then print. Okay, and just for fun, I had this thing down here. It's called. Oh no, I removed the stuff. Oh, okay. It's fine. Cout endl each time. Okay, I'm gonna call the function endl each time, which and it returns how long it takes. Cout endl at end. Okay, so if we try this, let's just look at what endl each time does. Endl each time is. Okay, this is don't worry about what this chrono thing is. It's basically a timer. The thing to look at is this. What does that do? All right, everyone I think everyone did it at the same time. But yeah, you print the first 100 integers, including 0 with an integer, print once on each line. Okay? Fun thing about the endl is a new line character plus this thing called flush. Anyone want to guess what flush does? Yes?
Is that what triggers it to actually print to the console?
Exactly. All right, flush triggers, tells it to print the stuff to the console. So what does this do? It prints to the console line by line by line every single time. As opposed to this one, Same thing, but instead you're putting the new line character without the flush, and you only flush once at the end. All right, which one do you imagine is faster? The second one, right? Okay. Now, to be fair, my computer is kind of weird, so I don't really know. Oh, no. Oh, I know why. I know why. I can't print this immediately. I have to call the functions first. So int a is equal to that, int b is equal to endl at n. So we call the two functions first, and then we print the amount of time they took. So a and b. Don't name your variables a and b. And yeah, so you can see the second one is significantly faster. Okay? Okay, now, to be fair, how much faster? Probably a little faster, but not like too much faster. Out of habit, you'll still see me type in endl, but if you ever go to a toxic online forum known as Stack Overflow, if you write code which has endl in it, people will people will not care about anything else other than that single line. Okay, so just FYI, if you're in like a high performance area, don't use endl too much.
That said, if you're not in a high performance area, it actually might, despite all the Stack Overflow users, it might still be better to use endl at the end of every line. And the experience that inspires that is, especially if you're in 106B, in your assignments, it's pretty much best practice to always put endl at the end of the line. Because when you don't, it can sometimes lead to bugs that are really hard to debug. So if you're ever in a situation where you're sort of having a weird like printing error in one of your 106B assignments, check whether you're putting endl at the end of each line, because that's likely the reason.
Mm-hmm. Yes. So sometimes you'll say, oh, I printed everything correctly, but it's not showing up on my console. Well, the answer is, have you tried using endl instead? And you'll see the stuff on the console. Okay? Now, there are some operations which will automatically trigger flush. Okay? One of these operations is if you call C in, then it will automatically flush C out. That makes sense because the user can't really type in anything until C out has printed everything, right? Okay? Cool. Is that it? Should I go more? I kind of want to talk more. Questions? Yeah, okay. Let me close all these tabs. They're kind of getting on my nerve. Okay. Yes.
So if just the new line character doesn't flush automatically, is endl like a special string, or is it?
Ooh, great question. Great question. And see, add these like amazing animations. So wasted. Okay, manipulators. So these are just special like keywords. If you insert them into the string, they change the behavior of the string. Endl is one of these characters. Essentially, if you put in endl, it basically is the same as, hey, print a new line and also flush the string. Okay? Is it a constant? Are these constants?
That's a good question.
Or like they're like enumerations, right? Maybe.
I think enums.
Enums. Okay. Yeah. We'll talk about what enums are next time, but yeah, these are like just constants. Okay. So.
So there's like a different alligator operator implementation which takes like a manipulator instead of just a string.
Exactly. Yeah. We'll talk about how to write the operators later. Good question. So endl is a manipulator, flush is a manipulator. With manipulators, you can do weird stuff like this. Spaces, fills, you can make everything look fancy. These are easy to Google, so we're not going to talk much about them. Question, yeah?
So actually, it turns out manipulators are functions. So that's kind of
Oh, these are functions?
Yeah.
Oh, cool. Okay, so I guess what the alligator does is it looks, oh, there's a function. Let me call it. That's probably what it does. Yeah, question? Yeah.
Is there a standard buffer size for string streams? And what happens if you try to, if A, you fill up the buffer, does it automatically flush? And B, you try to write a string larger than the buffer?
Ooh, good question. There definitely is a maximum size, and you can actually get the size. There's actually a way to get the size. There's like something limits max size of a thing. Yeah. What happens if you override it? Anna, do you know the answer? My guess is undefined behavior.
Yeah.
Yeah.
Oh, I think if you override, like if there's some natural default size, that'll likely act as a vector would, and it'll increase the size. So you would likely only override it once you ran out of memory.
All right. Any other questions? I think I'm pretty set. Well, so some of you left before I gave you your homework assignment, so this is kind of pointless. But yeah, I guess which one is best? This one's kind of cool, but it uses vectors. This one's kind of lame. No, okay, no, this one's pretty interesting. Okay, so given an input stream which looks something like this, don't need to do error checking. Print the end time. So there's a start time, there's a duration, there's an end time. Basically, print the end time. Parse that, print the end time. Okay? So you'll have to use string streams.
Did we have a question?
Yeah, do all the manipulators work for all the streams? Like, does your weird thing which like gives you just space, does that work right on like a network stream in addition to cout? Or
Good question. Not all of the manipulators work. So, for example, for like input streams, for output streams, not output. For input streams, you can't do endl,
you can't do any.
and you can't do endl because like you can't really read it. You can't really read a new line, right?
But I mean, even for like different types of output streams, like if it wasn't cout, if it was I don't know a file or something, would these all work? Or
File I think would work. For endl, file would work because it's the same concept
I'm
where.
not talking about endl. I'm talking about these ones.
Oh, these ones.
Generally, so it's
think so.
actually, it's sort of interesting. We're hiding a bit of sort of the class details. So it turns out all these sorts of different streams fall under different types of classes. And there's an OStream class, which OString stream is a specific subset of. And so depending on where the manipulator is defined, then it can apply to like all of the OStreams, or it can only apply to say the OString stream.
And that'll be checked at compile time.
Say that again?
That'll be checked at compile
And
time.
that'll be checked at compile time, exactly.
Also, yeah, check it out. So if you go on the C++ documentation, it tells you exactly which ones you can use. Okay, so yeah, you can all Google these. And of course, don't memorize these. Really, how you use these is you suddenly think, oh, my input is so ugly. I want to make it beautiful. Then you Google OString stream manipulators, and then this chart appears, and you look at which one you want. Okay, don't memorize these. No one ever memorizes these. So there you go. Okay, I think I'm mostly set. There's nothing.
I have one question for you guys before we leave in that case. So Avery mentioned really briefly that there's not only the OString stream and the iString stream, there's also just one string stream that combines both input and output. So can someone tell me why, if there's something that does both of these anyways, why would we ever use an iString stream or an OString stream? Why not just use string stream everywhere? What do you guys think? Yeah, let's go.
I think does it lead to like memory loss, because by default it's going to presume that you're going to both read and write, but like you might not want to do both.
Yeah, wait, so if I could paraphrase that, it'd be like, if you know you only want to do one, then you don't need the one that does both. Sort of. Yeah, exactly. And then what were you guys going to say? Sort of similar things? Yeah, similar things. Exactly. Yeah, so I guess to sort of put that in terms of the C++ philosophy that we were talking about, even though we can use the string stream everywhere and it would work perfectly fine, functionality-wise, in fact, there's no difference whatsoever. Well, no, that's sort of a lie. There's a slight performance difference and a slight memory difference. So this goes back to one style point, which is explicitly stating intent. That was one of the like 6 bullet points that we wanted to point out, which is that when you're writing code in C++, you sort of want to state your intent of what you want to do with the object. And then the other part is that there will be some minor performance benefit by using a more specific one. Yeah, so sort of intuitive, but just another reminder that sort of with all the different options, you want to ask yourselves, when do I want to use each one, and when do I want to use like the more general one.
Right. Okay, and then we're basically done, but what I did not cover was basically, I'll go over this next time. Basically, it shows you why Cin is a nightmare. Yeah, okay. And like really like innocuous code like this, which is what I assume if you didn't know about strings, this is what you would write. This does not work, particularly because that alligator operator only reads white space separated tokens, okay? So we will talk about this next time on Tuesday. All right. Next time what we will do is we'll talk about types. We'll talk about the modern C++ types, including pair, tuple, more fancier types. We'll learn about auto, and then we'll also implement getInteger, which is probably the hardest function to implement in the Stanford library. Okay. See you next time. Yeah, no problem. Thanks for coming.